Welcome. Thank you all for joining this webinar about charging batteries from solar energy. My name is Clemens Valens. I work for Elektor, and I will be co-presenting this webinar with Dan Holt from Microchip. Dan Holt is the one who put this class together, and he knows everything about our subject. So hi Dan, how are you today?
I'm good, you?
I'm fine, yeah. The weather here is not very sunny, but maybe it's better for you.
Yeah, I'm in San Diego, so we've been dealing with a heat wave. It's been in the 90s here for the last couple of weeks, which is hot for us.
Oh yeah, we had that a few months ago, the heat wave. It's gone now, unfortunately.
Mm-hmm.
Okay, well, this webinar is intended for people interested in using solar energy. We all know that solar energy isn't always available due to clouds, and sometimes it's even night. And sometimes, on the other hand, there is way too much of sun. In this webinar, therefore, we will look at how to store solar energy in batteries so it can be used when there is no sun. This webinar is an introduction to a Microchip University course on this subject, and the link will be shown at the end. The webinar is divided into blocks, several blocks intended to give you an idea of the complete class. So this is not a complete full webinar. You have to take the class at the Microchip University to see it all. After each block, if needed, a few points will be highlighted. Maybe if there is a question, we will answer a question. So don't worry if you can't follow along with the presentation. You should take the real class when you have the time for it, and as it will take at least 2 hours to do so. We only have 30 minutes. And when you do the class, you will be awarded a certificate for those who are into that. At the end of this webinar, there will be time for questions. You do this by typing into the, I'm not sure if you can see it, the lower right-hand corner in the Q&A chat box. This webinar is being recorded also and will be available afterwards on the Elektor TV channel for replay. Like I said, it is a very popular subject, so don't talk any longer. Let's get started right away. I will do this by starting the presentation video.
Hi there, my name is Dan Holt and I'm an FAE here at Microchip Technology. I spent years helping customers design their battery-powered products, including those that use solar panels as a charging source. Today we're going to dig into how you can specify and design a charger that will extract the maximum power from your panel while safely charging your batteries as well. This class is meant for hardware and firmware engineers who are interested in creating a system to recharge their cells or packs using power from the sun. While it might seem trivial on the surface, dealing with the wide dynamic impedance of panel voltages and currents while simultaneously providing safe charging profile for your chosen battery chemistry makes this design a bit complicated. My goal here is to bring you up to speed on the basics of solar panels and how to best extract power from them. I will also be giving you tips and suggestions on how to deal with the dynamic impedance that panels present to the input of your charger circuit. While you won't need prior experience designing with solar panels to understand this class, some prior experience with rechargeable cells or taking the class titled Battery Charging Fundamentals is recommended. So exactly what are you going to get from this class? First, we'll review a number of examples of solar panel applications from microwatts to megawatts. Next, we'll look at the different types of wafers, their characteristics, and how they're built up into panels. We will then discuss sizing of both the rechargeable battery and the solar array to charge it. And knowing the size of the battery and array, we can then compile a list of charger requirements, discuss a few of the most common charger topologies, such as buck, boost, and flyback. Then spend the remainder of the time looking at a series of available reference designs scaling from solar harvesters to microinverters. Let's dive in and start with a few examples of solar applications to give you a high-level appreciation for the wide range of power that can be achieved with solar. This section includes panels that are most often mounted outdoors and reasonably well aligned with the sun. This first range here is what could easily be called utility scale power. These very large arrays are built with no other purpose than to deliver power. There are hundreds of examples found around the world where land is cheap and the sun is plentiful. Here in the Southwest of the United States, where I live, the climate in the deserts provide an excellent environment for utility-scale installations such as this. The next size range could be called commercial or industrial scale. These 15 to 500 kilowatt arrays are commonly found on rooftops and parking lots, providing both power and usable shade. These are commonly designed to offset the power usage of the facility itself, as overgeneration doesn't typically provide a huge incentive unless the regional cost per kilowatt hour is high, and the grid owner purchases the power at more than wholesale prices. Our next size range applies to residential scale applications. These 2 to 25 kilowatt arrays are designed to generate the same number of kilowatt hours per year historically used by the home, averaged year over year. With an ROI of 8 to 12 years, these systems are very cost effective for those who plan on living in their homes long term, and typically have an electric bill averaging more than $125 a month here in the US. This is a picture of my own roof where I installed the system myself. It's not as hard as you might imagine, and the fact that my roof is nearly flat makes it that much easier to get around for sure. This started out as an off-grid installation, but I moved it on-grid a few years back. Getting even smaller, we now get into either mobile or semi-portable scale solar panels where the number of unique applications really explodes. Here we have consumer applications such as RV battery recharging and commercial applications such as radar speed indicators, remote weather stations, street lighting and signage, and industrial applications like remote sensors and condition monitors. These next examples include portable applications where the location of the panel is often shaded or even indoors. At only 1 to 25 watts, we really see a lot of consumer-type devices here. These include portable batteries, car battery maintainers, and solar landscape and area lighting. On the industrial side, there are remote sensors, condition monitors, and lighting applications as well. Finally, we get into panels that are so small that we should change our title from charging to harvesting. These panels are often found in indoor locations where the light intensity is 300 times lower than direct sunlight. We will dig into this more later, but harvesting can be even more challenging as the output voltage of the solar cell can drop to less than a quarter of the full sun voltage. So hopefully this quick introduction has already shown you how many different solar power domains exist and a few examples of each. Now let's transition into the terminology you will need to know when designing with a solar-powered application. Before we go any further, let's define a few of the key terms often used when discussing solar applications. The first of these relate to the panels themselves. The most fundamental piece here is the wafer. This is the processed silicon that is used either directly for large-scale panels or is cut into pieces to build smaller panels. A panel is an arrangement of series and sometimes parallel connected wafers that is held in a protective frame and usually contains two output leads, positive and negative. An array then is a group of two or more panels connected in series and parallel combinations depending on the needs of the charger or inverter. One of the most common acronyms you will hear is MPP, or similarly MPPT. MPP stands for the maximum power point, and it represents the voltage and current combination where the panel puts out the maximum power based on a specific set of conditions. The blue lines on the graph here represent the voltage times current, and you can clearly see that the peak of the asymptotes for each of the solar input levels. If you're not centered on the asymptote, then you're not gathering the maximum power available by the panel. Maximum power point tracking, or MPPT, describes the process of dynamically tracking the maximum power point over a wide gamut of conditions, including illumination and temperature. We will discuss several tracking methods in a later chapter. Two more terms you're going to see relate to the mechanical orientation of panels, and this is azimuth and elevation. Azimuth refers to the location in the sky that you're facing. So if I'm facing due south, so I have 0 degrees from due south, or I can be slightly west or slightly east. That's the azimuth. Elevation refers to the angle of the panel off of the flat surface. So the angle of a roof can be discussed in both terms of the azimuth of it, as well as the angle or the elevation of the panel. Two more terms you'll commonly see when discussing solar is lux and lumens. Lumens refers to the total light output that a light source generates. So a flashlight can have a lumen rating, and that's just the total amount of light. A lux rating refers to the amount of light hitting 1 square meter of a surface. So a lux is 1 lumen of light on 1 square meter. So you can get a little meter like this, which is going to measure lux, which is just the amount of light hitting an area at one point, and then mathematically extrapolate out to what that would be for a meter.
Okay, I stopped the video here for a moment, and maybe this was quite a difficult part with all the terms and terminology you have to learn before you can do this.
Yeah.
So maybe then you would like to add something?
No, I just, the reason I put this in right at the beginning is there is so much specific vocabulary that you're going to come across as soon as you start looking at panels. And we'll be talking more in the next couple modules about, how to read a data sheet and how to read the labels of a panel, for specification purposes. And if you kind of need that background of the vocabulary just so that you can, know what you're looking at and understand the terms. So we'll get into that more here in a bit.
Yeah, it's always difficult in the beginning. Okay, then we can continue with the presentation.
Great.
Here you can see a stack-up view of a wafer and all the layers involved. The active layer of the wafer includes P-type and N-type silicon, which are stacked to form a depletion region at the p-n junction. The top layer is an N-type material doped with phosphorus, which allows for free electrons to exist in the otherwise stable covalent bonds in the silicon matrix. The bottom layer is a thick p-type material doped with boron to provide excess holes for the free electrons to bond to. The resulting depletion region is normally a steady-state region where the free electrons are mated with free holes, so no buildup of negative or positive charge is detected without additional energy input into the system. No voltage will be present on the electrodes that connect to the top and bottom layers. In the presence of photons of light, the phosphorus electrons are broken free from the boron holes in the depletion region, which allows them to migrate to the p-type region, resulting in a buildup of negative charge on the top side of the junction. The bottom of the wafer is built on a conductive material, which sends the positive charge out to the positive lead. The negative charge is collected by a series of thin conductors on the surface to form the negative connection. These conductors will naturally shade some percentage of the wafer, so there's a balance between shading of the underlying silicon with the impedance losses in the positive conductor structure. The remainder of the construction is related to protecting this delicate wafer material from the elements so it can survive for 20 plus years in direct sunlight. The stack is placed on a base material and overlaid with a cover glass and anti-reflective coating. If we connect leads to the top, which is negative in polarity, and the bottom, which is positive, we can see that the resulting open circuit voltage of this p-n junction is roughly 0.55 to 0.65 volts in full sun, and this drops off in less bright conditions. So starting off indoor, you can see the voltage is only about 120 millivolts. And then as we slowly move outside, you can see that in the deep shade area here, we're looking around 0.4 to 0.5 volts. And it's only when we transition into full sun here that we get to back up to 0.6 volts plus. So you can see there's a really heavy dependency on the forward voltage of the panel, especially when you get into really dark situations where the voltage just crashes. Now, if we short out the panel and put it in full sun, you can see here we're getting about 1.6 amps or so. You can see as we slide over into the shade here, the deep shade, we're only getting about 0.3, 0.35 amps. And then as we transition into the doorway of my office inside, you can see at this scale, the 10 amp scale, we basically dropped to nearly zero, the measured milliamps. If we do switch it over into the milliamp mode or microamp mode, you can see we're getting about 3 milliamps of current in a normally lit office environment. So you can see the dramatic difference between 3 milliamps and 1.6 amps in full sun.
There was a question coming in that I am not sure how to answer. Then, are you going to discuss 3-4 solar cells and the difference in efficiency between 3-4 and silicium cells?
Yeah, I don't talk in this particular class too much about the advances. I do have a chart that's in there from NREL, which does show the overall progression of solar efficiencies over time. And it does show multi-junction, which is what the 3-5 combination, which is it's kind of what they use in space as a multi-layer, multi-junction panel. So in those cases, you actually have the 3-5 material on top, and then you have a base material of silicon, and so you're basically capturing different wavelengths of light and providing a higher efficient result from that. So we don't see that in the residential side of things right now. It's more of an eclectic, high efficiency, high cost. So the economies aren't quite there yet to do this at a large scale, but that's certainly something they're pushing towards, because you can get that much more efficient use of the sun. Right now, we're kind of stuck in the 22% efficient range, and they're trying to make the next leap by having multi-junctions to provide more efficiency.
Yes, this webinar is more about using solar cells and not so much as explaining all the differences, etc.
Yeah. This is as deep as we went as far as the science, let's say, of the panel itself.
Okay, thanks. I will continue the video.
Okay.
Determining the battery capacity in watt hours is a critical piece to a successful product, which utilizes solar recharging. Being blunt here, you can't rely on the solar panel to provide significant power consistently. A dark, stormy day, or even a stormy week or two, could very well drain your batteries to the point where they don't provide power through the night. If your application is critical and downtime is not an option, such as this road safety sign, then you will need to give yourself plenty of power to ride through the worst possible dark, cloudy weather your location can expect. This is clearly a reason why solar power is not relied on extensively for power in many safety applications in northern latitudes with stormy winters. For less critical applications, the choice is yours to determine the number of dark days you can survive before your device loses functionality. In all cases, you will want to take the long-term RMS power in watts multiplied by the number of hours or days you need to survive. The resulting watt-hour value is the guide to your battery size selection. In our second example, we had a camera system drawing 378 watt-hours per day, multiplied by 5 days, giving us 1,890 watt-hours needed. Selecting a battery with at least this amount of stored charge will guarantee your system to remain powered until more solar energy is available. Keep in mind as well that the aging properties of the battery as yet another reason to add additional capacity. Also, the stored watt hours in the battery needs to translate into usable power for your system, so be sure to understand how the efficiency of your design changes within the working voltage range of your chosen chemistry. And speaking of chemistry, you'll also need to look carefully at the environment this battery will experience based on your use case. Batteries located outdoor in their own enclosure can be subject to very cold and very hot condition. Your chemistry of choice needs to be able to handle this wide range while discharging as well as charging. Lithium-ion based chemistries don't typically handle charging when cold or hot. Charging a lithium battery when it's below freezing causes plating of the anode surface, which causes a permanent reduction in the anode surface area, and is not reversible. So clearly you never want to have this condition happen even once. It is possible to use the first available charging energy from the panel to purposefully warm the batteries in your enclosure before applying the charging current to the battery itself. Be sure to carefully read the datasheet and preferably discuss the application with the battery manufacturer to confirm the battery will operate as expected. Alternate chemistries such as lithium iron phosphate and others might offer better temperature ranges at the expense of power delivery. For some low power applications in extreme environments, it is possible that the use of a lithium doped supercap could be a good alternative to a standard battery, as they can have a wide charge and discharge temperature range from -40 to +85, while simultaneously maintaining a reasonably low leakage as well. Now let's discuss how we should size a solar panel. We already know that the quoted power output of a panel is based on overly idealized conditions. We also know that deep shade reduces power output by at least 10x, and dirt and debris reduce power as well. At the winter equinox, we have the worst case situation to survive. The days are the shortest, lowering the time to charge, and the nights are long, which requires more from the battery. The sun is further away and its elevation is the lowest, reducing the irradiance or watts per meter on the panel. The likelihood of cloudy weather is high, causing solar output to drop to 5% or less compared to clear skies, and the chance that snow could obscure the surface, and the result is really low power input to the power output ratio. Our previous section discussed sizing the battery on the assumption that the panel could be nearly useless for days or even weeks. Once the sun does come out, the next question is, how long do we expect the battery to get fully recharged? If we think about a UPS keeping power to our computer alive, we normally think about how long it will last during a power outage. What we tend to ignore, however, is how long it will take to recharge. If the power comes back on, should it only take an hour or maybe 24 hours before it's ready to keep your systems running during the next outage? In our situation, we have it even worse, as the product is always powered by the battery, and we are playing catch-up to recharge the battery while simultaneously powering the system. And of course, we can only really charge during the hours of the day when the sun is directly on our panel. The panel needs to provide substantially more power than the RMS power of the system to be capable of fully recharging the battery. So taking the worst case time of year, generally the dead of winter, and imagine the situation where we just came out of a dead battery situation. How much battery capacity do you want to have recharged by the end of a good day of sun between storms? This is one way to decide on the size of the panel you should select. To determine how many kilowatt hours you can expect in a particular location, you can use a website like the one provided by NREL, the National Renewable Electric Laboratory. From this website, you start by entering your location via zip code or GPS coordinates. It will then show you the location of the nearest weather station and let you select what legacy or historical data source to use in the calculations. Next, you enter the installation details, including array power, panel type and efficiency, system losses, and the panel angles and elevation or tilt and azimuth. There are more advanced parameters available as well to refine the inputs here. Let's enter a 4,000 watt peak array just to get a starting point. Also here we will enter the module type, array type, expected system losses, and the tilt and azimuth. The information icons give detailed explanations of each of these entries. Once we submit the form, the website pulls up historical weather data for the region, and along with the specs and installation details provided, it will give you a month-by-month kilowatt-hour estimations, along with the totals. As you can see here, this 4,000 watt array will produce 6,274 kilowatt hours per year. You can also clearly see here that the expected solar radiation per day, per meter squared, is as low as 3.12 in December, compared to the 7.71 in June, a 60% reduction in power input. Here you can see the month-by-month expected output in kilowatt hours, and for a grid-tied system, the value of the power based on your entered price per kilowatt hour. This can also be used to determine your system's ROI if you're thinking of going solar. So taking all this into consideration, we need to decide how big of a solar panel or array we need to provide the example product with recharging capacity after a fully dead battery situation in the winter. From this graph, you can see that a 4 kilowatt hour array gives us 301 kilowatt hours on average in the month of December. So dividing by 31, we can expect 9.7 kilowatt hours per day of power on average. Returning to our battery size calculation page, we can see that we will be selecting an 1890 watt hour or larger battery for the system to give us 5 days of runtime with no sun. So to recharge this battery in a day, we will need at least 1890 plus the daily power requirement of 378 watt hours. Assuming these and 85% charging efficiencies, we will want an array that will produce at least 2600 watt hours of power. Our proposed 4 kilowatt hour array will produce 9700 watt hours per day, so clearly we can scale that back a ways. Working backwards and iterating on the website, it turns out that we will need about 1200 watts of panel to produce the 2700 watt hours of power. 3 standard 400 watt panels will easily provide the power needed.
Okay, let me just interrupt here. I changed the microphone. Some people were complaining about my sound. If my sound is better now, please let me know. Also, as people are asking all the time, yes, this webinar will be available for replay afterwards. We will post it on our YouTube channel. There is no PDF presentation. You have to go to the Microchip University to do the whole course. And there you can watch it at your leisure and do all the exercises, etc. Okay, thank you. We go back to the video.
Okay, so at this point we have the solar array and battery sized to provide continuous power to our system. From here we can work on specifying and designing a charger to make all this work together. Our first step is to gather all the requirements we need based on the chosen components. From the battery datasheet, we know the key current specs including the pre-charge current, constant current, and the termination currents, and key voltages including the pre-charge threshold voltage and the constant current, constant voltage threshold. You'll find that most often a solar charger's current will be nowhere close to the battery's fast charge, as the battery's charging capacity is likely much larger than the solar output power. From the solar panel datasheet, we get an estimate of the MPP voltage, current, and power, as well as the open circuit voltage of the panel. If you dig in the datasheet, you will see the expected curve showing actual output based on lower illuminance. You can use the illuminance data you got from the website earlier to estimate the peak output power, and you will get into your charger. If there's a chance that you will have an external power source, such as an additional solar panel or an AC wall power, then you will need to keep these sources in mind as you specify the charging power handling. Okay, so now that we have all these requirements figured out, we can make a design document that includes the solar array peak outputs, as well as all the key voltages and currents required to properly recharge the selected battery chemistry. The last key piece we need to learn about now is how to implement an MPPT algorithm to maximize the power from our panel. Let's focus on maximum power point tracking, or MPPT, here for a minute, as we're gathering the requirements for our charger. There are many ways to actively track the maximum power point of a panel array. A few of these include perturb and observe, incremental conductance, open circuit voltage, and short circuit current. There are many more proprietary and patented methods you can find as well. It is important that at this stage to decide which version you will use, as each of these requires a different hardware interface, including current and voltage monitoring, and even short circuit FETs. Let's review the pros and cons of these approaches. The method I've seen most often is called perturb and observe, or P&O. To use this method, you measure the panel voltage and current at time t0 and multiply to give you the baseline panel power. The hardware necessary here is generally a high-side current monitor IC with a low impedance current sense resistor. The panel voltage can be sensed with a simple voltage divider as well. Let's apply the P&O algorithm to a system that is currently up and running. The red dot here represents the current operating point of the panel on the IV curve, and the blue dot shows the active location on the power curve. If we draw lines from the red dot, we can read the voltage and current we would get from the voltage divider, and the high side and current we would get from the voltage divider, and the high side current monitors using the micros ADCs. Multiplying the voltage and current gives us the current panel power, which is represented by the blue dot on the power curve. At this operating point, it is clear that we should reduce the panel voltage to get closer to the maximum power point of the panel. We can see this visually, but the routine has no idea where we are on this curve. We could just as easily be at this point here, needing to increase the voltage. So step 2 in the perturb and observe routine is to adjust your inner loop reference up a notch, which puts us now at this new operating point. As you can see, we clearly have dropped over the edge of the power curve, with the panel voltage rising slightly and the current dropping off significantly. Doing the math on these new current and voltage readings, we can see that our power output is now at 41.6 watts, which is lower than the 50 watt baseline. We can't just assume here that going lower gets us more power, because again, for all we know, we could have been at the peak already, and going up or down would result in lower power output. So for the third step of the perturb and observe process, we adjust the reference down a notch below the original baseline and measure power again. Here we see that our numbers have improved. The current has increased and the voltage has slightly decreased. Our power at this operating point is 55.2 watts, which is the best of the 3 operating points. Now our firmware knows that the panel output power is higher when operated below the baseline middle value. In firmware, the output of the MPPT routine is simply a direction flag, so the charging state machine knows which way to go to get more or less charging power. It will also flag that you are already at the maximum power asymptote, which is the most common result. Note that this whole process takes place in less than 100 milliseconds. So as lighting conditions change, the process can track changes and make small adjustments to the operating point. The size of the increments is generally very small, as you don't want wild swings in voltage or current. Now, what I've shown you here is a huge exaggeration in the step size of the operating point, just to make it easier to demonstrate. More realistically, these increments from baseline should be more like 100 millivolts or less. I think you can appreciate that the beauty of using P&O is the simplicity of the implementation and the accuracy of the result. You are measuring real power from the panel and making a determination based on these values. You also get the input voltage, current, and power data for analytics purposes, including input to output conversion efficiency data, assuming you have voltage and current monitoring on the battery as well. The disadvantages of this approach include the cost and power dissipation of the current sense function. While a voltage sense is as simple as a voltage divider or ADC input, high-side current monitoring isn't particularly cheap to implement and represents a continuous power drain as well. Another disadvantage is the speed of the tracking function. To obtain a new dataset, 3 separate readings must be taken. Depending on the speed of your converter, the size of your capacitors, which have to settle before taking a reading, and how much averaging you implement, the state machine can take hundreds of milliseconds to get a new result. In this section, I'll be showing you a series of both official and unofficial reference designs you can use as a starting point for your specific project. These designs are not available as purchasable reference designs from Microchip Direct, but the complete design package is available for download, including the schematics, the board layout, the design files, and Gerbers. We have the Windows PCBS GUI, we have the MIDI circuit simulations, and Excel design calculators. If you're looking for a 5 to 40 watt solar charger, this white paper reference design might be a good fit. As you can see here, this is a synchronous buck reference design with a 6 to 35 volt input handling on both the DC and solar inputs. The 4 18650 batteries can be arranged in series and parallel arrangements right on the board, or you can connect to an external battery pack via a header. All of the techniques described earlier in this class for startup behavior, MPPT tracking, and battery charging are implemented in the provided firmware. A full PC-based GUI is also available over the I2C interface header, and the UART is sent over USB for simple printf-style debugging and status updates. Looking at the block diagram for this design, you can see that there is a lot going on, so let me break it down a bit. There are 2 types of inputs this board can handle, both solar and direct DC. These are safely brought together with the DC input taking priority when connected. The Mic 4605 MOSFET driver connects the CPU to the high and low side MOSFETs, and each channel is individually controlled by the CPU. The output current is measured by a high side current monitor, and battery isolation disconnects the topology from the battery using a PFET transistor. Looking at the PIC16F1769 CPU, we can see there's a lot going on inside. This analog-intensive part was designed to handle constant on-time, fixed frequency, and resonant topologies. For this design, the key requirement is the ability to handle 2 different inner control loops with their own specific compensation networks. These error amplifiers are implemented using separate internal op-amps. So when a DC input voltage is detected, the converter will assume it can deliver the battery's peak constant current value programmed. In this case, the battery current is used to close the inner loop. When only the solar panel voltage is detected, then the panel voltage is used as the high-speed inner loop. The panel voltage is then controlled by the MPPT routine along with the battery charging state machine to deliver a charge to the battery. Here is the actual schematic of the CPU and power stage. Let me quickly highlight each of the blocks so we can see how each matches the block diagram. The first block here is the input mux where the DC input and solar inputs are combined, with the DC input taking precedence. The second section includes the dividers that bring the high voltage signals into the ADC inside the processor. The next section is the synchronous buck topology, including the gate driver. and the high side current is measured with an op-amp based current mirror or a high side current monitor IC. Here's the output isolation FET and control, and the output connector and battery holders with their routing resistors, which allow flexibility in series and parallel combinations. Finally, we have the heart of the design, which is the PIC16F1769 CPU. The analog and digital peripherals are completely configurable, and this arrangement shown is just one possibility. Zooming in a bit, here we can see that we have two air amplifiers that each have their own external compensation components for Type 2 compensation. Looking just at the PIC, you can see that the 10-bit DAC outputs are used as the reference set points for the air amplifiers. These outputs directly control the panel voltage or the battery current, depending on the input type connected. The output of each air amplifier is compared to a programmable ramp generator for voltage mode control, with the output of the comparator telling the complementary output generator to end the current switching cycle. This all repeats at the switching frequency of the converter, which is configured by firmware during initialization. On the second page of the schematic, we have a few miscellaneous functions to finish off the design. These include the power supply for the CPU, which can be powered by either VN or vSolar or VBAT, whichever is higher. We also see the PIC kit interface for programming and debug interface, and the I2C interface, which allows the PC-based GUI to program, calibrate, and monitor the system while delivering charge to the battery. You can connect using either a PIC kit serial or via USB connection using our MCP2221 converter. This converter provides a virtual UART and I2C port to the computer over USB. That's as detailed as we'll go on the schematic. Now let's take a look at the PC-based GUI. So this is the GUI that pairs with the firmware to provide calibration, configuration, and live data showing the MPPT and charger routines in action. These tabs allow you to navigate the GUI to configure, calibrate, and control the charger remotely. The Configure tab allows you to enter the key battery parameters, including the chemistry, the various voltages and currents for that chemistry, the number of cells in series, and the allowed charge time. This Calibration tab allows you to calibrate the battery voltage and current, as well as the input voltage channels. While charging, the Profile tab shows the basic battery voltage, current, and pack temperature. And finally, the most interesting of all is the MPPT Solar tab. This page includes all of the live panel and battery voltages and currents, the MPPT state machine values, and the MPPT result indicating the direction for higher power. In this case, it is indicating that more power is available if the panel voltage is dropped. The graphs show the data for the entire charge cycle, in this case almost 20,000 seconds or 5.5 hours. The next page of this module includes a link to download the design files for the schematic and PCB, along with the firmware for the PIC16F1769. Also available there is the PC-based GUI I just showed you, and just a reminder that this is a white paper design that you can build for yourself. It's not available as an official reference design for purchase. You can contact your local sales support member for more information on the design.
We have reached the end of the presentation. Thank you, Dan. That was very interesting indeed. Here is the link. Well, let me put on a slide with a bigger link. So you can go to the Microchip University. Here it is.
For the sake of time, that was about 1/3 of the content. So there's a lot. We had to kind of skip and jump through the material, obviously, because we didn't have an hour and 50 minutes to watch it all. But yeah, just to say that that was an overview of the class, and there's certainly a lot more content there, and that digs in the details. So you can see that on the actual Microchip University class.
Exactly. Like I said in the beginning, when you complete this course, you will get a certificate. I did mine, and you can. I put it on the left corner of this slide. We can now go to the questions.
Yeah.
If anyone has questions, you can type them in the chat box on the right bottom corner. Then I will switch to Q&A mode. Dan, I think you had another demo in your hand or on your desk.
Yeah, I have the there were several demos that are in the class. The one I showed in that one is this one. This is the little 30-watt charger reference design that can use a couple 18650s to charge, or in fact, you can put another battery holder on the back and actually have 4 18650s on this particular board. Form factor. Of course, you can always add a bigger pack on the outside. In the class, I also talk about this reference design, which is a harvester. This one lets you just pull power out of an office like this. We're talking 40 microamps. It's very, very low power. But indoor, there's a whole module on just this. In class, there's a module on that board. And then finally, there's this big guy here. This one will go up to 400 watts. It's just a single phase, but you can configure it a number of different ways. And it's using, again, that same processor that's on the other design, the 30 volt version. So these are all non-official reference designs for Microchip. So the design files are there on the class. You can download all the tools, the GUI, the Excel, all the firmware, and the PCB, the PC firmware. And from a question earlier, all of that is in, the board layouts are all done in Altium Designer. So they're not in KiCad.
Okay, so is an MCU sufficient to implement MPPT, or do we need more of a DSP?
Well, no. In fact, the smallest microcontroller can do this. One of the things about solar is that nothing really changes that fast. So as long as you're in a control loop, and I have a whole module on control loop for power control loop control for this sort of design, where because you can have something fly by like a bird, which can crash your input voltage, you do need to have the control loop looking at input voltage of your panel. And if that doesn't make sense, then that's a kind of a detailed power supply conversation. But I do have that in the class. But the MPPT routines happen very, very slowly. There's nothing that needs to happen really quickly when it comes to sun. So like I use an 8-bit microcontroller on both of these designs. This is an 8-bit PIC16F1769. It updates the perturb and observe algorithm about 10 times a second, and that's way more than enough. It will adjust and track within a couple of seconds to big step functions. So no, you don't need to have a lot of horsepower.
Good. Another question. How do you find the right angle for the panel?
Oh, okay. Again, unfortunately, there's a whole module on talking about angles, and I have drone video showing my roof from all different angles of the sun. The NREL site will give you some input on that. Ultimately, unless you have a big tree or some other reason that the sun isn't symmetric around, let's say, your installation place, you just want to point your panel south, and then the angle of the elevation of your panel ideally is something around the angle of the elevation that you are currently at. So you can look in San Diego, I'm at about 32 degrees, and so 32 degrees would be kind of ideal. But the whole module that I have in there in the class shows the fact that depending on where you are, like in San Diego, if I put my panels at 45 degrees, which is what I do in the winter, because the sun only goes up to 32 degrees in the sky in the winter, that's great. But in the summer, the sun comes up at 135 degrees in the morning. It actually fires at the backside of my panels until almost 9 in the morning. And then at 9 in the morning, then it finally starts to hit the front of my panels if I leave them up 45 degrees. So there's a lot of non-ideal things about the way the sun actually moves in the sky. And as you start to dig into this a bit, watch my class, I have a 15-minute module on it. It talks about where the sun is in the sky and how to adjust your panels. Or, in most installations, you don't adjust them throughout the year. So how to choose the best crossover between those two. And ultimately, it comes down to that winter environment where, in a fixed installation, you've got to have batteries charging as quickly as possible when the sun does come out. If you're in an application, like a remote sensor, that sort of thing. Home residential, most people just kind of slap them to the roof on the best angles they can and scale the number of panels to get the total power per year or per month that they need for their system.
Yes, I've seen that video, and it is indeed very interesting. I can highly recommend that for 15 minutes worth of, that's good quality. Actually, these are 3 questions. What kind of protections do you use to cut the current?
Oh, interesting. Yeah, that's something that you have to. It kind of depends on the application. If you're talking about like a small panel, such as this, okay, probably the worst thing that can happen in an outdoor environment would be some kind of lightning strike, in which case you're probably going to lose everything unless you put some pretty serious like transient voltage protection device to ground on, which is what we have kind of in a home environment or in a commercial scale. If you're talking about a much smaller panel where it's just like more of a consumer device, then the key thing there is just to have some kind of over voltage that can handle the steady state. So I talked in the class about how when you freeze a panel, and so I actually freeze one, and you can see the voltages and the currents changing. When panels get really cold, the forward voltages get really high. And so when the forward voltage is high, and maybe your battery's fully charged, so you don't need the power, you have basically an open circuit or an open circuit condition on the panel at the input of your power supply. And if you don't design it to handle the absolute cold and clear environment, where the panel voltage can go a lot higher than the label voltage says. It doesn't talk about peak voltages usually. It just talks about a maximum power voltage. That's one of the protections that I talk about in the class as well. So if you cannot use a fuse, what is your option? I guess I would need to know a little bit more about the application, specifically, what the power levels are to suggest a particular safety mechanism. You just need to understand what the solar panel is capable of in terms of voltage and current, and what your system's capable of in those worst case conditions.
Okay, the next question. Do you have experience with harvesting solar power on floating areas and the impact of waves and water drips?
Are we assuming maybe this is a boat?
Probably. This looks like
floating areas, impact of waves. Okay, so yeah, if you imagine this thing's on a boat and you're bouncing around and such, yeah, you definitely again need a control system that is using the panel voltage as the inner control loop, so that you have enough just simple analog bandwidth to track the fact that you may have variability in the input. Panels are not maybe as sensitive as that, though. And if you're in such rough conditions that you're all over the place, you probably aren't getting more than, like he says here, maybe harvesting power. So you're not probably going to be tracking it all that well. Most of the time, if you have a panel or just a wafer, if the sun is anywhere close to the center point of the panel, you're going to be getting full power, and it slowly drops off as you get off axis. So, if you're just bouncing around a little bit, you're probably not radically changing the amount of input power to the panel.
Okay, here we have another interesting question. Is the MPPT mandatory?
Okay, so again, more detail in the class. If you don't have maximum power point tracking, the key is that the forward voltage of your panel drops as the intensity of the sun drops. And so two things can happen. If you just try to take panels into a battery charger and the charger just expects the input voltage to be like wall powered, then what happens is if the input power to your solar panel drops below the charging power that's being delivered to the battery, basically the input voltage will come down to a point where it suddenly goes all the way to zero, because the power supply is going to go to full duty cycle and try to dump all the power it can. And so you really have to have a solar designed charger. You cannot use just an off the shelf battery charger that would just otherwise normally try and convert power. Now, if you had something like one of these, we call them PWM chargers, which is a silly comment. It's not PWM at all. It's literally as simple as almost a relay, where it just connects the panels directly to your batteries, which can work just fine. What that doesn't do is it doesn't use the maximum power point of the solar panel. So you're getting some percentage less, 5, 10, 20, 30% less power from the panel, because you're just forcing the panel voltage to equal the battery voltage. And so as long as that's being tracked, then you can track the the current and the voltage of the battery. And so you can get a charge out of a PWM charger. You just don't get anywhere close to the maximum power point. And again, those power curves you'll see in the data sheet.
Another question about charging. Does the controller has to control know about the battery you are charging?
Yes, the answer is absolutely. I have two other classes that talk about the fundamentals of battery charging and battery pack design, which talks about the battery management and all that as well. But if there's no way to safely charge a battery if the charger itself doesn't know what those parameters are. So you need to know a series of the voltages. And so one of the modules we watched today talked about you need to know what the pre-charge voltage is. You need to know what the constant current and constant voltage thresholds are and when to stop charging. And so if you have a lead acid or a metal hydride or a lithium iron or lithium iron phosphate battery, they all have different chemistries, they all have different voltage pivot points and currents. And so it is fundamental to charging to know the details of your battery. At least as important as knowing the solar panel parameters is the battery charging parameters, so that you know that you have a proper fit in your charger.
Then this one, it's also dealt in the class. What about the partial panel shading?
Yeah, so panels. So if I take this is a 4x3 array here that's all in series. So if in the class, I show a larger panel in actual sun and kind of a hyperlapse kind of thing where you watch the sun come up or go down and you see it just slightly cover up the corner of one of a series of panels. And in doing so, if they're all in series, this completely destroys the forward power of the panel. So think of these as diodes in series. If I take one diode and I basically shut it off, I lose the entire array. So if I have a tree that's kind of shading one part of a particular panel, that's catastrophic to the output power. You'll see a 10x decrease in panel if I did that. So if you have let's say a residential installation where you have a lot of panels on your roof, each of those panels is actually divided into thirds, and there are bypass diodes in those. And so those bypass diodes allow the panel to be broken up into thirds. And if the forward voltage across one group, let's say one group of series connected cells get shaded, it allows the voltage basically to jump over that one and keep going down the string of your array. So what's common today in residential is we now use either microinverters, and we kind of have this discussion a little bit as well in the class, but microinverters versus DC-DC optimizers. So if you just string all of your panels on a roof in one series string, and you cover over a few, again, you can have panels that reduce the power of the whole string, although the diodes do protect you a certain amount from that. It just will kill the forward voltage that your inverter is getting. With optimizers on each panel, either a DC-DC or a direct DC to AC, now each panel operates in its own world, delivers the maximum power point onto the string or directly onto the AC bus. So that's kind of the conversation there.
But that's also a much more expensive solution, I suppose.
It depends. For my system, I use the DC-DC optimizer version, and that version there, you do have a $60 for me module that goes on each panel, and so that's, if you look at the cost of that versus the efficiency it gives you. The other beauty of DC-DC with an inverter at the end of the string, let's say down in your garage on the side of your house, you put the inverter separate, and the inverter is always getting the power at once. So it can tune all the DC-DCs to deliver exactly the voltage and currents that it needs to work most efficiently. So again, those are very efficient systems, and it puts the inverter at a lower cost point, also in a cooler part of your property, versus having a microinverter bolted to the back of a hot panel. So I'm not a microinverter fan myself.
Okay. Another question about batteries. Charging lithium-ion batteries at low temperature seems to be an issue.
Yes, it is. in general, lithium-ion batteries are not designed for low temperatures, and they will plate, which will kind of destroy them or reduce their capacity pretty quickly. So there are other chemistries. Lithium iron phosphate in general is a lot better, and that lithium iron phosphate is also becoming much more common for bulk storage applications. You can get those cells. You can build your own packs of lithium iron cells. There are some more eclectic cells. If this is more of an industrial or commercial installation, where cost isn't as critical because performance is very much is critical for you. There are some more eclectic technologies out there. You'd have to kind of go digging around to see what's available in the capacities that you need, whether that's a small cell or a big block. But take a look at lithium iron phosphate as an option because I've definitely seen it used in colder applications. Another way to deal with it, honestly, depending on the battery size, is to use some of your solar power to physically warm the battery, if you can have it in an enclosure, to warm the battery up a bit before actually charging. And hot is another issue too. Lithium iron phosphate does better at high temperatures, where you don't really want to charge a lithium ion battery to full charge while it's really hot, or store it in that condition. And that really degrades the cells quickly. So the other thing about having a smart battery charger is we can measure the temperature. These boards have temperature sensing on board. You should have a temperature sensor in your battery, and you can change the charge profile. Whether you top off the battery when it's hot, probably not a smart thing to do. Maybe you only charge it to 90%, which will save the chemistries from being damaged. So you can get more elaborate in your charge profiles if you have control of the charger itself.
Okay, thank you. We're almost at 5 o'clock. We will do one last question. And then, yes, unfortunately, there are many other questions. We do not have the time to answer them all. Mm-hmm. So let's do this last question. And then everybody moves over to Microchip University to take the course.
Yeah.
Does it make a real sense to use MPPT with a small panel installation?
Mm-hmm. So yeah, 140 watt panel with a 60 amp hour lead acid battery. So that's a good size battery. Again, I guess you could say it's a cost comparison between the difference in efficiency that you would get from the panel versus the cost of the panel itself. So yeah, you do need to kind of understand how much more expensive that MPPT charger is, and would it make sense to just double the amount of panel that you have, or if you're panel limited, then and getting power when you have some sun is really important, then a maximum power point tracking charger would really be valuable to you. It's not absolutely mandatory. It's just much more efficient.
Okay, well, thank you very much, Dan. This was really interesting. Like I said, and like Dan said too, there's much more in the full class. This is only a quarter maybe of the whole class.
Yeah.
So you really should go over to Microchip University and take the class. I saw a question that somebody couldn't access it. It is open to everybody. You only have to create an account on the Microchip website, and then you can take all the courses there.
Yeah.
No special, nothing, and it's all for free. Yeah,
yeah, it's all free.
Yeah.
All the design files for all these are also free as well.
Yes, and also to repeat once more, the boards that we showed in this presentation, they are just, you have to build them yourself. You cannot buy them. These are just, the design files are online. You can download everything for free, but you will have to build them yourself. Yeah. And I don't know if you can find Superfire batteries yourself. I would never use batteries with a name like that. But yes, it's your homework to build one of these boards yourself.
Yeah. That's it.
Like I said at the beginning, this webinar will be available in a few days on the Elektor TV channel on YouTube, and then you can watch it again and again and again as many times as you like. You can stop it and you can think about it, etc. The next Elektor webinar will be about the wireless technologies and applications, and is scheduled for October the 13th, which is in about 2 weeks. So hope to see you there again. Once again, thank you very much, Dan, for doing this webinar with me, and thank you all for attending. Goodbye.